Today we're going to start talking about subgrid-scale parameterizations, or today specifically about subgrid-scale fluxes, or SGS fluxes for short. So all our models are relatively coarse. For example, in terms of resolution, for example, from large eddy simulation models, or those that are used to study turbulence in atmospheric boundary layer, for example, they may have resolution of maybe 10 meters in the order of 10 meters, maybe 200 meters or so. And our cloud models, like squall lines models, thunderstorm models, they can be few hundred meter grid spacing. Our regional models can be several kilometer grid spacing or so, and global models can be much coarser resolution still. So, but we have lots of processes in atmosphere that happens in much smaller scales than we can represent on our grid. And this is a constant dilemma what to do with that. If we cannot represent certain process, we don't have enough resolution for it. Even though we know the equations that govern those phenomena, we need to somehow still represent them in our models using so-called parameterizations. And parameterizations usually work by basically it's some submodel of our main model that relates this so-called subgrid-scale fluxes, for example, or to resolved field resolved by the model. And one of such very important processes is turbulence. And on a space of grid, like if you have some flow, turbulent flow, well, maybe it's not crossing, but you get the picture. So we have some turbulent flow, and our grid spacing our grid cell can be as big as this. And of course, we need somehow to represent this transport within that grid cell. First of all, one of the important processes, like from a dynamical point of view, is dissipation of kinetic energy. And dissipation of kinetic energy is done by viscous forces, viscosity. But those scales, when dissipation actually happens, they are very small. They literally like millimeters or so in a scale. And our grid, of course, is much bigger than that. And also we need this kind of, but there is this energy transport because of the dissipation of kinetic energy through many scales, and we need to parameterize it somehow with some kind of diffusion process. Also, we may have, like if we just have, say, jet and it transports some scalar quantity. Of course, in nature, it doesn't really just follow streamlines. It's actually, there is some process of diffusion by the small scale turbulence that we also need to represent somehow. So there are many processes related to turbulence that we need to describe in our models that have relatively coarse grid spacing. So let's start from diffusion. That's a basic process. So diffusion generally is described by so-called Fick's law. Which was proposed back in 19th century by, well, Fick, yes. So it basically states that flux of some scalar phi equals to minus diffusion coefficient d, d phi dx, where d is diffusion coefficient with units, say, meter square per second. And minus here is because, well, if you have, say, phi versus x, so that your phi is increasing with x, then of course we know from our experience that diffusion should bring higher values to well, low values of quantity phi r. So d phi dx for this line is positive, so flux should look this direction. That's why we have this minus sign in that. Okay, so for this fixed law, so by analogy, we can, so this fixed law is perfectly fine for scalars. So it's for scalars. Now for momentum or for velocity, so let's disregard any density of air there, like just assume that it's a Boussinesq approximation, density is 1. So let's say it's water or something, or air in boundary layer of atmosphere. So from for momentum, if you write it's like that, like say it's a viscosity minus viscosity du, say like in 3 dimensions, like some velocity component du dx, let's say. Generally it's not correct. Velocity is special. Why velocity is special? Because there is this case when this formula obviously does not work. For example, if you have solid body rotation, so your fluid, let's say, is rotating, like as a cylinder. And with constant angular velocity everywhere. So it's solid, that's why it's called solid body rotation. So obviously, if it's solid body, there is no relative movement of velocity or momentum relative to each other. And if there is no relative movement of parcels of fluid relative to each other, there is no diffusion. It's like constant. Diffusion, when something is constant, d phi dx should be 0. And so for this case, this one is actually won't be equal to 0. There will be diffusion. So it's an error. In order to, you can actually show that, for example, that u component for this rotation, if there is some radius r from the center of rotation, equals to minus y omega, where omega is rotation frequency or velocity, and v equals to xy times, well, yeah, so the distance not r, let's say it's x. Yes, r with components, its components x and y. And from that, du dx equal to 0, but say du dy is not equal to 0. And diffusion is happening in 2 directions. So, but we notice that if we consider it like the following, du dy plus dv dx, for solid body rotation it's 0. So from which we conclude, so there is no then diffusion. So from which we conclude that for diffusion, for diffusion your flux should be equals to nu du dy plus dv dx. So see, this is why diffusion of momentum is different, should be treated differently than diffusion of any passive scalar, like, or active scalar, but scalar, say temperature, water vapor, and so on. So let's before we move forward, let's we need some mathematical notation. We will use extensively index vectors as using indices, so that, for example, vector u is just a vector with coordinates ui, where I equals from 1 to 3 in 3 dimensions. And so any vector, we will write vector as using this index. Now, scalar product, for example, of two vectors, say vector u and v, let's call scalar product equals to u, obviously, like from definition of scalar product, it's sum over I from 1 to 3 ui vi. So we would, if we would use lots of scalar products in this lecture. So generally, in order to avoid writing this summation sign, Albert Einstein came up with this kind of convention that people now use everywhere in all sciences, that basically omits this summation sign, but everywhere if you see two indices repeating, like here I, it means that its summation index there is implied. So in Einstein notation, it would be just written uivi. So as long as you see this same index, you assume that it's actually summed along that index. But ui plus vi, so summation, this convention only concerns itself with kind of multiplication, not like if you have sum like this, ui plus vi, it's just one vector plus another vector. It's not really, it's not summation. Each component of vectors are actually summed up. So this one is equals to uy plus v1, u2 plus v2, and u3 plus v3. And it's just still vector. So you see summation, this convention only acts on products. Another thing that it's used is for derivatives. So say du for partial derivatives. So du dx, say dui. And by the way, here if you have like ui, uj, two different indices, it means matrix. It's a matrix with indices u1, 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 v1, I mean u2, u1, u3, and so on. So it's a 3 by 3 matrix. So you see, because there is no repeating index here, it's just matrix. So derivatives like this is you can have like derivative for first component with respect to second component of coordinate and so on. So this one is just matrix. But if you write dui dxi, summation is implied. So this one is a scalar product of d dx operator, or this del operator, times ui. So it's just scalar product of del operator with vector. You see this index is repeating, so it's a du1 dx1 plus du2 dx2 plus du3 dx3. So this is just divergence. So it's equal dui or dxi. So instead of writing all this, the whole sum, we just use this notation and then we're done. So this is just similar things can be, but a little bit more difficult is for vector products. We won't use any vector products in this lecture, so I won't explain them. Yeah, so I think that's sufficient for our lecture. Okay, so we can define for momentum we have like momentum equation which says dui dx dt, sorry. So it's i's component of momentum plus uj d dx j u I. So this is advection. So you see there is summation on j index. J equals changes from 1 to 3, but there is no summation in index I. Equals to minus dp over d dxi. You see it's gradient in the same direction as u. That's why it should be ddxi. I assume that rho equal to 1. It's incompressible fluid. And plus, now here we should write diffusion. So diffusion is modeled as the following. It's a divergence of Subgrid-scale stresses. So ddx dx j tau ij, where tau are subgrid scale, or just tau are diffusion or viscous stresses. And for molecular viscosity, tau ij equals to minus nu times minus 2 nu times strain tensor. This strain tensor, and this is, so Sij is a strain tensor. So it's basically some matrix that has the following form: Sij equals the one that is becomes 0 for solid body rotation, 1/2 dui dxj plus duj dxi. There is no summation here, even though you have repeating index I, but you see they're not multiplied, or they're not applied as derivative. It's just plus here between them, so there is no summation over that index. So this is a strain tensor that we're going to focus on, and this one is just stress, and this is definition of those fluxes. So let's see if we, for example, substitute this, and also another question that we have is, let's assume that flow is incompressible and density is constant. So it's dui dxi, well, it's the same thing as duj dxj. Here's summation over index I in here, and summation over index j, it doesn't matter, equals to 0. So this is very simple form of non-divergence equation. All right, so now let's write this term here. So minus ddxj. So here you see there is summation over index j. And the result is a vector along the I direction, because only I index would survive. And of course it should be I here, because it's for I's component of momentum. So tau ij. So if we write it using this definition, we have 2 nu, and the 2 will cancel. So just nu. That's why it's actually defined 2 here. And this 1/2 is defined like, it's like for symmetry. So we have nu dxj dui dxj plus duj dxi. And now if we actually do some math here, so let's differentiate. We have here is second derivative d dxj dui dxj plus nu d dxj duj dxi. So let's look in here. We can so this guy, nothing can be done, there's just a second derivative, right? Second derivative of ui dxj squared. Now this guy, we can actually flip the partial derivatives order. You know that partial derivatives can be actually swapped like that. So we have the same as d dxi, so we put this one first and then this one second. duj dxj. And here, so this is derivative of this guy, but this guy, it's a summation over index j now, and according to this equal to 0, so it will disappear. So then we have this kind of normal conventional form of diffusion that if you rewrite it component by component, say for u, first x component, this would look like as nu d2u1 over dx1 plus d second derivative u1 over dy1 plus squared plus second derivative of u1 over x dx2 here dx3 squared. So this is the same thing written just in component explicitly in this form. So and this is kind of looks like normal diffusion operator that we're used to, but again, you see, even though it's like that, it's only consequent that our divergence equal to 0. So that's only true for in this case. When divergence equal to 0, then we can write in this form, technically speaking. Other than that, we need to use this definition and use don't kind of cancel this term, because it's for compressible fluid, for example. This term is not cancelled. Okay, but that's a little detail. So now, so what's the problem then? We have the numerical, we have actual diffusion process. Why we don't just use in our model on the right hand side these terms like that? We know viscosity coefficient for air, and why don't we just in models just compute it like that, and that's it and done with it? The problem is that diffusion acts on very small scales, and for our grid spacing, if we use this directly, like using our finite difference representation of the second derivative, for example, right? So we have this new second derivative of phi dx square can be represented like nu phi, say I plus 1 minus 2 phi I plus phi I plus 1 divided by delta x square. So why we don't just use it with this coefficient? The problem is that this coefficient for air, nu, is something in the order of 10 to the minus 5 meters squared per second. It's very tiny. And now it's divided by delta x square, which is for delta x in the order of, say, 1 kilometer. It's going to be 10 to the 6. So this thing in front of phi would be 10 to the minus 11. And this term would be so small compared to everything, and times phi. So this d phi dt will be equal to like 10 to the minus 11, this order of phi. So that would mean that characteristic time of diffusion on this grid using this new coefficient would be in the order of 10 to the 11 seconds, which is like very long time. So we cannot do that. So generally for atmospheric models, we should ignore diffusion, molecular diffusion, because it's very small for our phenomena. And of course, it's determined by so-called Reynolds number. We probably know that from some other class, that turbulent regime and molecular and laminar regime are dictated by so-called Reynolds number. And laminar regime is the one that controlled by viscosity, and turbulent regime when it's not controlled by viscosity, but controlled by so-called inertial forces. And so Reynolds number transition between those two usually in the order of 1000. This Reynolds number, it's basically Reynolds number is defined as some characteristic velocity by some characteristic size scale of the flow divided by molecular viscosity. So for atmosphere, this Reynolds number is very, very large. It's mostly because D is very large. So, and nu is very small. So Reynolds number is very large and means that the flow is not viscous from atmospheric model point of view. However, we need to preserve viscosity in one process that it's actually important, even though it happens on very small scale. It's so-called dissipation. And we're going to talk about that a little bit later. So now, as we introduce this kind of convention and our primary laws that describe diffusion of momentum of scalars, let's talk about turbulence. So we established that our Reynolds number for atmosphere is very large, so our flow is almost always turbulent to various degree. So we need to describe this somehow. So we cannot describe it by molecular diffusion anymore. So how we can describe this process, which is not resolved by our model? So this turbulence, let's say, is so small that it actually fits inside our grid box. For that, we need to describe somehow, find some parameterization or some parameterization model for subgrid-scale variability of our flow. And of course, we cannot do that deterministically. In terms of actual second by second flow structure inside our grid box or individual grid box, because we don't know that. But we can approach this problem from statistical point of view. We just assume that our flow, subgrid scale flow, has some stable statistical properties that we can use to derive some fluxes that we can then use in our subgrid scale model. So for that, let's use the simplest statistical approach. It's called Reynolds averaging. So for that, we assume that in our grid, that the flow in our grid box, U, let's say, or any quantity, U or phi or temperature, anything, can be viewed as a superposition of two regimes. One is resolved by the grid, or in this case, it's average of the grid cell, plus some perturbation. So this is grid scale, and this is subgrid scale, SGS. And we use just ordinary arithmetic kind of normal averaging without any weights, anything like that, any moving averages or anything like that. For that case, our first rule from that, if we now average this equation, we have U average equals to U double average plus U prime average. And obviously, because our average is just simple arithmetic mean, so it's summation. So this average guy is just a number. And if you average number, let's say number 5, you can average as many times you want, it's still number 5. So from that we actually postulate that average of average is equal to average. And if you do that, immediately it follows that average of any perturbation equals to 0. Well, makes sense. Now, that's basically the rule that there are several other Reynolds averaging rules, like for example, that derivative ddx of u average equals to ddx u. It's because derivative operator is actually linear. So in other words, that ddx of u prime, I mean like that, equals to ddx, according to this rule, u prime average, which is equals to 0. So now let's consider some kind of binary quantities which can be viewed as flux. So we have this, if we write our momentum equations in flux form, so we will have the following: u I d dt. Again, we consider the compressible fluid, so rho is equal to 1, plus ddx j uj ui equals to minus dp dxi, and plus molecular diffusion, which we, for now, let's ignore it. So now let's average this equation with respect to a grid cell. So let's derive an equation for grid cell. So for grid cell, we just need to average. So we'll have, according to our rule, Reynolds averaging rule, a term like this. Then we'll have a term like that, and then a term like this. So everything is nice. So let's look at this term a little bit more carefully. So let's consider this term. So let's substitute our definition. So it's a grid average plus perturbation times grid average plus perturbation. So let's multiply. It's ui average, uj average plus ui average u, well, here we need to maintain it, u j prime plus ui prime uj mean plus u prime u prime I uj prime, and it's average here, average here, average here, and average here. So if we use our rules, well, average of averages is just average. So it's ui uj prime average bar. Now this guy is just a number, it's average, it can be taken outside from the averaging sign, and average of perturbation is 0, so this guy will disappear and this guy also will disappear. So we have the following rule, and these guys we cannot average because, well, they only disappear if they're not correlated with each other, you know, from statistics. So this is so this term can be written now. So this equation can be written. So this is our grid scale. So this is for grid. This is what we resolve with our model. Equals to minus d pi dxi, and if we take this another term to the right hand side, we will have here minus d dx I u I prime u j prime. So this is subgrid scale, divergence of subgrid scale fluxes. So this is u I u J primes average equals to tau, this stress, subgrid scale stress. So this is SGS stress. And it equals to UI UJ averaged minus UI average UJ average. So this is these fluxes are called subgrid scale stresses, or also Reynolds stresses. So this procedure is called Reynolds averaging. So all you have to do now is to somehow represent these Reynolds stresses or the subgrid scale fluxes in terms of, well, information that we have. And the only information we have is grid scale information. So we need to deduce SGS information from grid scale information. So can we do that? Well, technically speaking, it's a very difficult problem, right? It's not necessarily that it's true that subgrid scale fluxes entirely depend on grid scale information. That may not be actually true. For example, let me give you an example. Let's say that you have lots of buildings on the surface and they generate turbulence, and then your grid spacing is much bigger than your buildings. And so your mean flow over those buildings and turbulence around these buildings will be determined by distribution of those buildings in subgrid scale, not necessarily on the mean flow which is following above. Of course, you can then deduce, because it will be some friction induced on that flow, you can have some measure of roughness of the surface and deduce fluxes like that, some model. So you can always find some model for phenomenon you want to describe that would kind of approximate your solution. But again, this relation is a hypothesis. It's not necessarily true for each and every case. In many cases, though, in a case that we're going to consider very soon, so-called inertial subrange turbulence, this correspondence is actually pretty much exact. So if you know some scale information about your turbulence, you can actually deduce pretty accurately the subgrid scale information from that. But again, it's only we just can do the best that we can do. And sometimes we just have no choice but to use some crude representation of subgrid scale process. Otherwise we're stuck. We cannot just give up and say, okay, problem cannot be solved, and we're just not going to do anything. So of course, we try to be as physical as possible, but sometimes a lot of hand kind of waving and involved in justifying this kind of transition from grid scale to subgrid scale. So one of the methods that is probably one of the most popular is actually you can write equations for the Reynolds stresses themselves. How to do that? Well, you have your original equation without these bars, and then you have equations for bars. So if you subtract one equation from another, you will have an equation for rate of change of perturbation with time. And now if you multiply it by another component and make it an equation like something like that, you will have prognostic, and then you average it. You will have prognostic equations for your Reynolds stresses that depend on some right-hand side, some terms there. And then you basically say, okay, I'm done. I can actually represent my subgrid scale processes with a set of another equations. The problem is that these equations for these Reynolds stresses will have not only Reynolds stresses on the right hand side, or some kind of binary products of these velocity components like here, but also triple products. So so-called second moment, or in this case this stress, actually depends on the third moment, or terms like that, ui, ui, uj. This is a function of this. And so if we would write equations for this triple product, triple moment, or third moment of velocity, on the right hand side there's going to be, as you guessed it, fourth order moments, and so on. So the process is basically infinite. So you cannot close the system. So that's basically the closure problem. How you close your system of equations to predict your variables, and generally number of variables that you need to predict should be equal to number of equations that you use. So that actually has, but you can of course parameterize or describe this again moments in terms of these moments, or even first moments like perturbations or variances and stuff like that. So that has been done. Those approaches are called so-called high order closure models, and we're not going to discuss them in any detail because they're pretty complicated. It would span several lectures just to describe them, like such models as a Miller and Yamada model and so on. So we're not going to talk about those. Those called high order closure. Like second order closure, third order closure. Second order closure means that there are like triple moment there that parameterize in terms of second moments, and third order closure, it's actually triple moments also predicted, and fourth order moments are parameterized in terms of second order moments and third order moments and so on. So those can be very complex, and you can actually derive those relationships using very high resolution models, so-called direct numerical simulation models that would get you some idea how to close those systems of equations. But we're not going to discuss it here. What we're going to discuss here is so-called first and half closure model, which is based on so-called prognostic equations for Subgrid-scale kinetic energy.